And then based on this session, based on chapter 2 in power diode, you'll see some classroom workbook questions also. Yes. We'll see what is the types of diodes based on applications. Okay. These are types of diodes. Types of diodes based on application. Based on application. The types of diodes based on application. Okay. So this concept important for theory concept. Then based on application, so many types of diodes are there. One is general purpose diodes. General purpose diodes. General purpose diodes. Okay. Go through with general purpose diodes. These general purpose diodes are implemented in order to use for, mainly these are used for high power applications. Mainly these are used for high power applications. High power applications. These are implemented mainly for high power applications and used 50 volts to up to 50 kV and used for a current of 1 ampere to several 1000 amperes of current. 1000 amperes. 1 ampere to several thousand amperes. For these diodes, okay, the turn off time is nearly equal to 50 microseconds. For general purpose diodes, the turn off time is nearly equal to 50 microseconds. Hence, used for low frequency applications. Used for low frequency applications. The turn off time is nearly 25 microseconds. This is nearly equal to 25 microseconds and used for low frequency applications. This mainly for general purpose diodes. Okay. All these are PN diodes only. All are power diodes only. But based on application, we are giving this classification. Then fast to recovery diodes. Fast to recovery diodes. This fast recovery diodes used for low turn off time applications. Low turn off time. Used for low turn off time applications. And these are used 50 volts to up to, these are used 50 volts to, these are used for a voltage range of 50 volts, these are used 50 volts to up to 50 kV we are using. 50 kV we are using. And these are used up to less than that 50 kV, up to these are preferred up to 30 kV. Okay. These are we are using up to 50 kV, these are used up to 30 kV only preferable. Then these are also used for 1 ampere to several thousand amperes. Several 1000 amperes, these are preferable. 1000 amperes, these are preferable. Okay. And these are 50 volts to maybe greater than 50 kilovolts also used, or you can give the range like this, 50 volts to in kilovolts. That depends on the rating, maybe changes. These are also used 50 volts to, the range is given in kilovolts. up to kilovolts also. Mainly that may be any range. Recently the range may be extended, manufacturing, the range is extended. That's why that is not the constant value. Okay. But these are also used 50 volts to in kilovolts. These are used 1 amperes to several thousand amperes. Clear? This is a fast recovery diodes used for this main point, low turn off time applications. Low turn off time applications. Its turn off time is in the range of, it is maybe in less than 25 microseconds. Less than 25 microseconds. That is nearly equal to 15 microseconds, or it may be 10 microseconds. Okay. That fast recovery diodes. Then the third one is a Schottky diodes. Schottky diodes. Okay. Schottky diodes. Where we can use Schottky diodes means these are used for high frequency applications. Used for high frequency applications. High frequency and low voltage applications. Low voltage applications. These are not used for high voltage, high frequency and low voltage applications. But point to remember, what is the difference between a Schottky diode and power diode, or a Schottky diode and PN diode? A PN diode is nothing but both the layers are semiconductor layers. But in Schottky diode, one layer is a metal layer and other one is a semiconductor layer. That's why it's a combination of metal and semiconductor layer. It's a combination of metal and semiconductor layer. This is anode and this is cathode. This is metal layer. This is metal and this is a semiconductor layer. A Schottky diode is combination of metal and semiconductor layer. Understood? Okay. Then metal layer means aluminum. Aluminum means conductor. Conductor means what the carriers? These are electrons. Carriers is electrons. Then here which is the majority carriers? Electrons. Majority carriers is. That's why in Schottky diode the total conductivity is due to only electron. Hence it is a majority carrier device. Yeah. Therefore it is a majority carrier device. It is a majority carrier device. Yeah. Majority carrier device. Yeah. Majority carrier device. And the conductivity is due to only electrons. And the conductivity is due to only electrons. And the conductivity is due to only electrons. Understood? Then the total conductivity is due to only electrons. That's why it is a majority carrier. This is satisfying, I told. All unipolar devices used for high frequency application. This is the reason. Okay. Because of aluminum metal layer, the minority charge carriers are less. When the minority charge carriers are less, then it is reverse recovery time is less. When the reverse recovery time is less, then used for high frequency application. This is what exactly a Schottky diode. Then another one is silicon carbide diodes. Silicon carbide diodes. Silicon carbide diodes. Okay. These are the specially designed diodes for limited applications. Mainly these are designed for ultra high frequency applications. Used for ultra high frequency applications. Used for ultra high frequency applications. Used for ultra high frequency applications. But only drawback of this diodes is these are costly diodes. These are costly diodes. These are costly diodes. Yeah, these points you remember with respect to types of diodes based on application. General purpose diodes are mainly implemented for high power applications. Fast recovery diodes also implemented with having some range is nearly general purpose diodes, but having the low turn-off time. That is a special feature. But Schottky diodes are implemented for high frequency applications, but the voltage and current ranges are less in the case of Schottky diodes. Cannot be used for high voltage and high current applications. But silicon carbide diodes are specially designed diodes implemented for ultra high frequency applications. This is the silicon carbide diodes. But these are implemented only for limited frequency applications. Limited applications only, not limited frequency, limited application. Used only for ultra high frequency applications. And this is the types of diodes based on application. Okay. With this, the concept with respect to power diode is completed. This knowledge is important to answer any questions for any competitive point of view based on the power diode. This is mentioned in the power diode concept is mentioned in the various competitive exams. You take GATE or IES or any PSUs you take, power diode concept is mentioned in the syllabus. Understood or not? Okay. Now with this knowledge, take workbook. In chapter 2, the concept is power diode. We'll see some questions. Okay. The topic covered in the power diode is construction and characteristics of a power diode. Based on that, we solve some questions. Okay. Understood? Okay. You take the workbook. Go through with the classroom workbook. The concept is chapter number 2. The concept is power diode. Topic is construction and characteristics of diode. Let you concentrate. Yes. The topic is construction and characteristics of diode. Topic covered. Construction and characteristics of diode. Characteristics of diode. This topic is given. This is concentrate on first question. What the answer for this first question? Consider the following statements with regard to power diodes. This theory question. Consider the following statements with regard to power diodes. First one. The breakdown voltage is directly proportional to doping density of drift region. That is, breakdown voltage is what it is given first statement. Breakdown voltage directly proportional to doping concentration. This is first statement. What is the second statement? Losses in the diode are less due to conductivity modulation of the drift region in the on state. Losses is less due to conductivity modulation. Due to conductivity modulation. Losses is less due to conductivity modulation. The third statement is the vertically oriented structure supports large blocking voltages. The vertically oriented structure supports large blocking voltages. Which of the above statements is correct? That's the vertically oriented structure. The vertically oriented structure. The vertically oriented structure supports large blocking voltage. Then which of the following statement is true? Which of the following statement is true? Okay. Tell me, which of the above statement is true? Breakdown voltage is proportional to doping. Can you accept this statement? This is wrong statement. I told you. If the doping concentration is increases, layer width is reduces, then blocking voltage capability is reduces. Understood? But here what is given? If the doping is increases, breakdown voltage also increases. Wrong statement. If the doping is increases, width of the layer is reduces. If the width of the layer is reduces means high blocking voltage or less blocking voltage. Less. That's why doping concentration is inversely proportional to the breakdown voltage. But it is given proportional. That's why it is a wrong statement. Losses is less due to conductivity modulation. Yes. Because of conductivity modulation. What exactly conductivity modulation? That I explained in double injection. Okay. Because of conductivity modulation only in the power diode, losses is less. But the vertically oriented structure supports large blocking voltage. It's meaningless. The large blocking voltage is supports because of the drift region only. Understood or not? That's why it is also wrong statement. Then according to the given options, which is the correct answer? That is second statement is correct. That's why answer B is correct. Answer B. For first question, answer B. That is 2 only the statement is correct. See the second one. This also theory question. A structure obtained by lightly doped N-drift region between the layers of a PN junction, a PIN diode is obtained. The structure is effective in making the diode supports large reverse blocking voltages, making reverse recovery process is slow, making the diode have high on-state voltage drop, reducing the voltage spikes during turn-off due to stray inductance. What it is given? A structure obtained by lightly doped N-drift region in between P and N regions. In between P and N regions, we are using lightly doped N- region. This N- region is nothing but intrinsic layer. Because of this intrinsic layer, which diode is formed? PIN diode. I told now, because of intrinsic layer, it blocks high voltage, high blocking voltage. That's why the reverse blocking voltage capability is increases. Then making the diode support large reverse blocking voltage. Then for second question, what is the answer? Answer A is correct. Making the diode support large reverse blocking voltages. Okay. Then we'll see the third one. Question number 3. Concentrate question number 3. For question number 2, answer A is correct. Concentrate question number 3. A power diode is in forward conduction mode and the forward current is now decreased. The reverse recovery time of the diode is TR and the rate of fall of the diode current is di by dt. What is the stored charge? Okay. Then what is the stored charge? Okay. A power diode is in forward conduction mode and the forward current is now decreased. The reverse recovery time of the reverse recovery time is given. Third one. What is the solution for this one? Reverse recovery time. Reverse recovery time is TR. And the rate of fall of diode current is di by dt. Rate of fall of diode current is di by dt. Diode current is di by dt. Then the question is asked, what is the stored charge? You calculate what is the stored charge, QRR. Then according to given options, you want to answer this. What is the first option? It is given di by dt into TR. What is the second option? It is given half into di by dt into TR. What the third option? It is given half into di by dt into tr square. Half into di by dt into tr square. What is the fourth option? It is given. Fourth option it is given as this half into di by dt square into tr. Half into di by dt square into tr. Okay, we know that. For this, you want to answer this one. Reverse recovery time is rate of fall of diode current. We know this. What is reverse recovery charge? 1 by 2 IRR into TRR. But in the problem, what it is given? 1 by 2 IRR into TR. Instead of TRR, you take TR. But you know this. What is IRR equal to? TRR into D. These expressions are already given. Then TR into di by dt. Then you substitute IRR in this equation. Then what you get? QRR equal to then 1 by 2 di by dt into TR square. Then option C is correct. Okay. These expressions you know now. Now I am substituting IRR in this equation. If you substitute IRR in this equation means TR into TR square. That is TR square. 1 by 2 di by dt into TR square. That's why for third question option C is correct. Okay. Then go through with question number 4. In the same concept. Question number 4. Is clear? Yes. Okay. Concentrate on question number 4. For a power diode, the reverse recovery time is 3.9 microseconds and the rate of diode current decay is 50 ampere per microsecond. For a softness factor of 0.3, calculate peak inverse current and storage charge. Understood? Given that, then what is the solution for this problem? For a power diode, the reverse recovery time is 3.9 microseconds. TRR equal to 3.9 microseconds. 3.9 microseconds. Okay. And the rate of diode current decay, di by dt equal to 50 ampere per microsecond. 50 amperes per microsecond. di by dt equal to 50 ampere per microsecond. 50 ampere per microsecond. Softness factor equal to 0.3. Softness factor equal to 0.3. Yes. Calculate peak inverse current. Calculate IRM. That is IRM is question mark. And calculate storage charge. And you also calculate QRR. Okay. Now, what is IRM? Here softness factor is given, reverse recovery time is also given. Then you know the data for T and TB also. Okay. Then first one. What is softness factor? Softness factor equal to 0.3. That equal to TB by TA. Softness factor equal TB by TA. Then what is TA equal to? What is concentrate on? What is TB equal to from this? TB equal to 0.3 times of TA. Okay. Then what is TRR? TRR equal to TA plus TB. No? Okay. Then TRR is how much? 3.9 microseconds. 3.9 microseconds. That is TA plus 0.3 TA. 0.3 times of T. Yes. 0.3 times of TA. Then what is TA equal to? 3.9 by 1.3 microseconds. Then TA equal to 3 microseconds. If TA equal to 3 microseconds, then what is first one? What is IRM equal to? IRM equal to TA into di by dt. 3 microseconds na 3 into 10 to the power of minus 6. What is di by dt is given 50 ampere per microsecond. Yes, 50 by 10 to the power of minus 6. How much we can get? 150 amperes. This is IRM. And also calculate stored charge. What is the formula for QRR? 1 by 2 IRM into TRR. Okay, 1 by 2. What is IRM? 150. What is TRR? The TRR is given as 3.9 microseconds. 3.9 microseconds. Then you simplify this. What you can get? The reverse recovery charge you can get. What the reverse recovery charge you can get? 292.5 microseconds. Sorry, micro. This is a charge na microcoulombs. We can get 292.5 microcoulombs. Understood? Okay. This is question number 4 based on this concept. Clear? But sir, you know another formula IRR equal to TRR into dI by dt. But why you are applying TA into dI by dt? But the data is given for TA. That's why there is a data is available to calculate TA. I told now, based on the problem, the required formula you can apply. Data is given to calculate TA. That's why don't apply directly. TRR, IRM equal to TRR into dI by dt. That is approximate formula. But why to go for approximation? Because the softness factor is given. The softness factor is given means to calculate TA, data is available. That's why you calculate exact value of TA. Then we can get this IR. Understood? If the data is not given to calculate TA, then you go for directly TRR into dI by dt in this formula. Clear? Then go for question number 5 in the same concept. The forward characteristics of a power diode can be represented by VF equal to 0.88 plus 0.1 IF. Determine the average power loss and RMS current for a constant current of 50 amperes for 2 by 3 of a cycle. Okay. Then what is the solution for this problem? Okay. The forward characteristics of a power diode is represented as VF equal to 0.88 plus 0.88 plus 0.1 IF, 0.1 IF, 0.88 plus 0.1 IF. Then for a forward current of IF equal to how much it is given? 50 amperes. Forward current of 50 amperes. Then you calculate average power loss and you calculate RMS current. This you want to calculate. Then for 2 by 3 cycle. For 2 by 3 cycle. Okay. Then first you tell me at IF equal to 50 amperes. At IF equal to 50 amperes. What is VF? You tell me. VF. VF equal to, that is at IF equal VF equal to 0.88 plus 0.15 into what is IF? 50. Then 0.88 plus this is 7.5 now. Then how much you get? 8.38. 8.38 volts. This we can get 8.38 volts. Understood? Then you want to calculate average power loss and RMS current for 2 by 3 cycles. Then what is the average power loss? You tell me. First one, average power loss equal to average power loss 1 by T integral 0 to T VF into IF into dt. Okay, but you want to calculate average power loss in 2 by 3 cycle na, that is 2 by 3 into T, that is VF into IF into dt. For 2 by, in the total cycle, for only 2 by 3 cycle only you can calculate, up to 2 by 3 cycle. Okay, then it is the time period. Don't change this one, this is time period. Then if you integrate and substitute the limits, what you can get? VF into IF into 2 by 3 you can get. That is 2 by 3 into, what is VF? 8.38 volts. 8.38 volts. What is IF? 50 amperes. Then you substitute, then you simplify this one. What is the power loss we can get? 279.33 watts. 279.33 watts. Then we calculate RMS current rating. How to calculate RMS current means? In RMS current also we calculate RMS current, IRMS equal to 1 by T integral 0 to 2 by 3 IF square dt whole to the power of 1 by 2. Then you simplify this one. What do you get? Root 2 by 3 into IF. Then root 2 by 3 into IF is how much? 50. Then you simplify that value, you can get 40.825 amperes. 40.82 amperes. This we can get. Understood? Okay. Like this we can solve. Clear? Yes. This IRMS equal to 40.82 amperes. Yeah, this is about how to calculate for a given characteristics, how to calculate average power loss in a 2 by 3. But if the question is framed calculate only on 1 by 4 cycle, substitute 1 by 4 here. Okay. Here also you substitute up to 1 by 4 cycle. That if it is not mentioned, calculate total time period means up to T you can calculate. Understood? Okay. That is question number 5 in same concept. See the question number 6. The same power diode concept. Yes. In a reverse recovery characteristics of a diode, the reverse recovery time is 3 microseconds and di by dt is 30 amperes per microsecond. Then the reverse recovery current is dash. Okay. Then what is the solution for this problem? A diode reverse recovery time is 3 microseconds. TRR equal to 3 microseconds. Then di by dt is 30 ampere per microsecond. 30 amperes per microsecond. Then what is the reverse recovery current? We know that IRR equal to TRR into di by dt. What is TRR? 3 microseconds. What is di by dt? 30 ampere per microsecond. Then how much you get? 90 amperes. The reverse recovery current is 90 amperes. Simple question. Understood? Here I am not using TA into di by dt because there is no data to calculate TA. If the data is given to calculate TA, then according to that you can do the problem. That's what I explained in the previous problems. Understood? Okay, this is about some classroom workbook questions based on power diode concept. Okay. I want to give some summary points with respect to power diode. Then with respect to power diodes, I want to give some power summary points. Then with that power diode concept will be completed. This is about classroom workbook questions based on this. Here I am giving some summary points with respect to power diode. Some summary points, important points I am giving based on these characteristics. We know that okay, if TRR is increased, frequency of operation is reduced. That is one observation. If you want to operate the device at high frequency with less power loss, then it must be designed with less reverse recovery time. That point to remember. To operate the diode at high frequency, to operate the diode at high frequency, to operate the diode at high frequency, to operate the diode at high frequency with less power loss, with less power loss, it must be designed with less TRR, that is less reverse recovery time. Another point to remember, we know the expression for QRR, you know the expression for IRR. QRR and IRR, that is QRR and IRR, depends on Depends on QRR and IRR. Depends on. It depends on di by dt. It also depends on TRR, and it also depends on IF, that is forward current. Very important point. It also depends on forward. From the equations, you know, it depends di by dt and TRR, but indirectly it also depends on IF. That means if IF is increases, if the diode rating is increases, if the diode is having high forward current, then what is the reverse recovery charge is also increases. If the reverse recovery charge is increases, what the reverse recovery current is also increases. But what is the reverse recovery time? Decreases. A high rating diode associated with high reverse recovery charge. Then then IRR is If IRR is increases, what the TRR is also increases. But frequency of operation is reduced. Frequency of operation is reduced. Important observation. Understood? Another point to remember. A high forward current diode having the forward characteristics are linear. A high rating diode, a high forward current diode, a high forward current diode, forward current diode, forward current diode having forward characteristics are linear. Characteristics are linear. Okay. Understood? These characteristics, these forward characteristics are having linear. Understood? But I want to give some list outs here. Generally, once the diode is designed, the manufacturer will specify some parameter on the data sheet. Then what are the specifications are given by the manufacturer with respect to diode? That specifications are given both under reverse bias condition and forward bias condition. With respect to reverse bias condition means specifications are with respect to voltage, because under reverse bias condition we don't have any current. Sorry. With respect to reverse bias condition, there is no current. The specifications are with respect to voltage only. But under forward bias condition means the specifications are given with respect to current. Okay, that is concentration. Concentrate. What are the specifications? Mainly points you remember. Specifications of diode. Specifications of diode. The summary points I am giving. Specifications of diode. In reverse bias condition. In reverse bias condition. What are the specifications of diode under reverse bias condition? Under reverse bias condition. Okay. The specifications mentioned under reverse bias condition is with respect to diode is one is DC blocking voltage. DC blocking voltage. DC blocking voltage. The second one is RMS recovery voltage. RMS recovery voltage. RMS recovery voltage. RMS recovery voltage, that is VRMS. Third specification is peak repetitive reverse voltage, VRRM. Peak repetitive reverse voltage. Peak repetitive peak repetitive reverse voltage. Repetitive reverse voltage. Reverse voltage. Okay. Then fourth specification is VRSM. VRSM. This is peak non-repetitive reverse voltage. Peak non-repetitive reverse voltage. Peak non-repetitive reverse voltage. Non-repetitive reverse voltage. Yes. Reverse voltage. The fifth one is, it is mentioned that peak non-repetitive reverse voltage. Okay, these are the voltage specifications given by the manufacturer under reverse bias condition. That is, Mainly this DC blocking voltage is, that is the maximum voltage withstand by the diode under reverse bias condition. That is the maximum direct voltage. This is a maximum direct voltage. Maximum direct voltage. Maximum direct voltage. Withstand under reverse bias condition. Under reverse bias condition. Okay. This volt, what is the significance of DC blocking voltage is useful to select a freewheeling diode. This DC blocking voltage is useful to select a freewheeling diode in power electronic circuits. It is useful to select a freewheeling diode. To select a freewheeling diode in circuits. That is in power electronic circuit. Okay. To select a freewheeling diode in power electronic circuit, this is more useful. This is more useful. Understood. Then what is the RMS recovery voltage? This RMS recovery voltage is useful to calculate the power loss. Okay. This RMS to select this selection will be, that is this RMS recovery voltage is useful to identify the power loss and to select a diode for rectifier application. To select a diode for rectifier. To select a diode for rectifier application. For a rectifier application. Mainly to select a diode for rectifier application we can use. Then what is the peak repetitive reverse voltage? This is the maximum voltage across the diode. This is the maximum instantaneous voltage across the diode. It is the maximum instantaneous voltage across the diode. But it is a repetitive voltage. Repetitive voltage. Then when this voltage will appear across the diode means during the operation of commutation circuit. During the operation of commutation circuit, this type of voltages will appear across the diode. During the operation of which one? Commutation circuit. This is we can define this is the maximum voltage across the diode, that you know down. This is the maximum voltage across the diode. This is the maximum voltage across the diode. There is a maximum voltage across the diode that appear periodically. That appear periodically in reverse bias condition. This is the maximum voltage across the diode that appear periodically in reverse bias condition. Okay, that point you remember. And this voltage is exist during commutation circuit operation. During commutation, this voltage will appear. But what is the peak non-repetitive reverse voltage? This is the maximum instantaneous voltage across the diode. This is the maximum instantaneous voltage across the diode, which is non-repetitive. It is the maximum instantaneous voltage across the diode under reverse bias condition, which is non-repetitive. Okay, note down this one. This is the maximum instantaneous voltage across the diode under reverse bias condition, which is non-repetitive. Then when these voltages will appear means during switching action, during opening and closing of circuit breaker, or during lightning strokes, these voltages will appear. That is during opening and closing of circuit breaker. Opening and closing of circuit breaker. These voltages will appear. Or during lightning surges also, these voltages will appear. Now, all these are the specifications of diode under what condition? Reverse bias condition. Now tell me, among all the voltages, which is the less voltage, reverse voltage under DC condition? This next one is Vrms voltage. Next one is peak repetitive reverse voltage, VRRM. Then next one is VRSM. Then which is highest voltage? Reverse breakdown voltage. Reverse breakdown voltage is the highest voltage. Understood? Similarly, what is the specifications of diode under forward bias condition? Specifications under forward bias condition. Under forward bias condition. What are the specifications of diode under forward bias condition? Under forward bias condition means which specification we can give? Yes, current value. Current. because forward bias condition there is a flow of current only. Then what the specifications means? Maximum RMS forward current. Maximum RMS for this note down. Maximum RMS forward current. Maximum RMS forward current. That is one specification. The next one is maximum average forward current. Maximum average forward current. Average forward current. Maximum average forward current. The third one is you also concentrate surge and fault current. Surge and fault current. Surge and fault current. Surge and fault current. The fourth specification is peak repetitive surge current. Peak repetitive surge current. Peak repetitive surge current. Surge current. Then peak non-repetitive surge current. Peak non-repetitive surge current. The sixth one is that is I square T rating. I square T rating or integral current square current. Integral square current. This one. Okay. This is different current ratings mentioned in the under specification of forward bias condition of a diode. This is maximum RMS current. It determines the conduction power loss. It determines conduction power loss. It determines the conduction power loss. It determines the conduction power loss. Okay. Then what the I square T rating? This gives to select a protecting element. To select protecting elements. To select protecting elements, this is useful. Protecting elements, that is fuse, all these fuse circuit breaker like this. If you want to select a protecting elements, then this I square T rating is more useful. Okay. This is about the importance of maximum RMS forward current is determines the conduction power loss. Okay. Then it also gives heat generated internally. How much? This gives the data regarding to heat generated internally. These are the specifications under forward bias conditions. These voltage specifications under reverse bias condition. This is the current specifications under forward bias condition. This is the maximum average forward current, surge and fault current rating, peak repetitive surge current, peak non-repetitive surge current, I square T rating, protecting elements. This mainly I square T rating is useful for. Okay. In detail about these ratings, you also study in thyristor also, that will be repeated in detail. That you will see in detail about that. But here just I am giving some introduction only. That you can't say. Here just I am list outing. Okay. What is the importance? Where you can select. What is the significance of each voltage rating and current rating? Understood? Okay. This is the concept of diode I discussed. With this, diode concept is, power diode concept is completed. In the next sessions, we'll start with, in chapter 2 itself, we'll start with the thyristor concept. Then we enter into the thyristor. Okay.